Now this is something that I want to mention right now. That is, as I mentioned, I'm tweaking this class. I'm starting a water management class with a hydrology 101. How many of you have taken a hydrologic class before? Here we have one. Okay, we have many. Okay, good. For those of you who haven't taken a formal class, I mean, this will be a very good how to start on with this with hydrology. You can. I'm starting this in this way because you cannot distribute water, or you cannot find ways to redistribute it or to quantify how much it is if you do not know how much it is. So that's kind of the start. Now, here we're going to be talking about the hydrologic cycle, and then some surface water and groundwater principles. Basically, hydrology, or when I talk to hydrology, this is just is the study of the water cycle. It is that simple. And because we're studying the water cycle, we're going to be studying about evaporation, precipitation, runoff, infiltration, and evapotranspiration, and other different aspects of the hydrologic cycle. I think you have heard about this since you were in elementary school, which that helps. But something that I also want you to know right now is this concept that is the water, which is the water budget. So P refers to precipitation, and basically this is the water that we are going to have. This is the water that is landing into our basin. Evapotranspiration is the water going up. Runoff is the water that is going from the headwaters to the sea or to a different place. Groundwater is the water that is going downwards, and changing storage is basically whatever water you have stored here, how this volume of water change with respect to the previous time step. Okay, we're going to see something like that when I use the ANFAR models. But basically, precipitation is the water that falls. How much water returns back? Well, how much water goes back to the atmosphere? That is ET. How much water goes down? That's groundwater. How much water goes horizontally? The runoff. And then, if you have any change of storage, how much that is? It is that simple. Precipitation. This is a water budget. We can also have some other inflows, and those inflows can be water imported from a different place, and that can be through aqueducts, through different pipes. So it will be precipitation, and here we can have something that is water that is imported. Okay? Oh, this is interesting. Go ahead.
So on the last slide, the groundwater, that's a static number.
No, it changes through time. So basically, if we're measuring every month, that runoff will be changing every month. All of those terms change. Well, in water management, we usually think it in terms of months, but it will change day by day. I'll tell you, it's just iterative. Just start with an initial value, and then with that value to start time one, and then what is the precipitation, what is the evaporation, and for that time step one, and then go to the second time step, and use some of the values of the previous one. It's just iterative. Okay. Now, drainage basin. So basically, a basin is the area where if it rains, all that water will converge into one place. Let me see here. So basically, you have this area, rains, and once it starts raining, all the water will drain into the rivers, and all the water will end up in an outlet, in the outlet of the basin. So the basin is the area where if it rains, all that water will merge into one place. That's the definition. So we will be, most of the times when we're talking about basins, the basin is the area, and that area encompasses how the water moves into one place. Now precipitation, there are different types of well, it's just water, it precipitates, but the how it precipitates is different. Usually these are the ones, the orographic one is the one that is more familiar in California. But this stratiform is when you have hot air and cold air. So this is cold air, and this is hot. So when it's hot and the two of them encounter, the hot air will go up. And when it's going up, it's kind of colding, or it's getting colder, and that's how it will precipitate. This one is the same. You have all the moisture here. So all the moisture is going in this direction. When it happened the same, see, the moisture moves up, and when it moves up, it just condensates. It gets colder. It's vapor that gets colder, and when it gets colder, falls as precipitation. This is actually what happened in California. So we have all this moisture, and when we have all that moisture coming in here, it will go up, and all this rain happen. Now we have all this rain. When this moves downward, it will kind of warm up again, and when it gets warm, it will not precipitate. This part here and here is called the rain shadow. So we have the first part, which is the wet front, and then when the air gets warmer is the rain shadow, and here again will precipitate again. Usually in the coastal range, it precipitates in terms of rain. Here in this part in the Sierra Nevada, it precipitates in terms of snow, and it precipitates in terms of snow because this is a higher altitude, and the higher altitude it gets colder and colder. Most of the precipitation of us come in terms of atmospheric rivers. So basically, this is a band of moisture, and this moisture will come here, will hit California, and will do all this event. These atmospheric rivers, or this, imagine a large amount of humidity coming through the atmosphere. So it's coming this large band of 100, 150, 100 miles, 200 miles. It's coming all that moisture. That amount of moisture is about 10 to 15 times the outlet of the Mississippi River. There is a large amount of water, and it comes through the air. 50 to 60% of the precipitation that we receive in California, it's through atmospheric rivers. So you can see here, one atmospheric river, another atmospheric rivers happen usually in periods of 2 to 3 days. So you can see we have high precipitation, and this is the cumulative precipitation. This line here. You can see that every time that we have an atmospheric river, we have one of these large steps. And precipitation, how do we measure precipitation? Well, we measure it in terms of how much it rains compared to time. So if it rains half inch in 1 hour, well, that's the intensity. If it rains 2 or 3 inches in 1 hour, that's a higher intensity. That's what we are estimating here. Frequency, we can record how, let's say, those intensities. How frequent, let's say, 1/4 of an inch falls. in a year? Well, we record all those events. If we divide the number of events by the total events plus 1, which is basically, this is simple statistics, then you get the frequency, how frequent this event happen. Let's say we have an event of 1 inch, 1 inch, 1 inch, then 2 inches, 4 inches, 2 inches. Okay, so the number of events here, we have 3, and the number of events, n, is equal to 6. How many times do we have the event of 1? Only 3. So in this case, the frequency of having an intensity of 1 inch per hour, it will be 3 over 6 plus 1, 3 over 7, and that will be, I don't know, somewhere in the round of what? 0.43, 0.46. .43. Okay, so this is how much rain throughout California. This is, I think, easier. So most of the rain falls where we have all this blue area. Actually, 80%, 90% of the rainfall in California only happen in that area. The remaining 10% of the rain happen in the yellow, green, and red areas. So most of the rain happen in, as you can see here, in the Sierras, in the coastal range, and here in the Klamath River. That's where most of the rain happen. Interception is basically, I mean, not all the water just falls into the ground. Some of the water will be catched by the canopy, by the plants. When they catch that water, some of that will go back as evaporation. So now we have evapotranspiration, and evapotranspiration is, okay, so we have precipitation, that's rain, and it can be in forms, precipitation in terms of rain, of snow. And then evapotranspiration is how much water the plants drink, the plants take, and send it back to the atmosphere. That's in essence what happened. We call it evapotranspiration because some of that water, in order for a plant or for us to provide water to a plant, we need to get wet the soil, to moist the soil. And when we are pouring water into the soil, it will go back again as evaporation to the atmosphere. So that's the part of the evaporation. Once that water permeates into the soil and it gets into the roots, so the plant just kind of grab it, actually drink it, then send it to the roots and move all the minerals upwards. That's the part of the transpiration. Have you ever put have you covered a plant with a bag? You just put a bag on top of, what happened? Fog? Yeah, it kind of sweats. That's the transpiration. If any one of you go to office hours, I hope you do. Basically, that's a plant that I have in my office. Happy plant. Sometimes it has this amount of water, and sometimes it has this amount of water. I mean, what happened? Magic! No, it was not magic. Basically, I mean, the plants drink all that water. So that's what's going on there. And also, so usually, okay, so now we have evapotranspiration, and that is that concept. We use a concept that is called reference evapotranspiration. And that is basically to have this, let's say a well-watered grass. Imagine a piece of grass, I don't know, 1 meter by 1 meter. And then we estimate how much water that piece of grass take. I hope it's not one from the Adivan. Well, that is the reference evapotranspiration we use as a reference of how much water takes the grass. And then we said, okay, with this grass, I know that this grass took, and I'm just going to say right now a number, 3 millimeters or a quarter of an inch of water this day. And then we use that as a reference to say, okay, what about how much water use, let's say, a tree of apples or a peach tree. So if the peach tree use, instead of a quarter of an inch, let's say half inch, so the tree use twice as the grass. So if it is using twice, then the Kc value, the crop coefficient value is 2. So whatever uses the grass times 2 is what is using, in this case, the peach tree. That is basically kind of how we are relating some of these evapotranspiration values to actual values in the for other crops. Now this is the reference evapotranspiration. Imagine that we have all California paved with grass. Everything is grass right now. Oh, I mean the realtor business will be happy, doesn't it? They just like to sell houses with green lawns. Okay, so this is how much water is taken in October 2012. Now, as we are, okay, what do you think will happen with evapotranspiration as the weather gets colder? Do you think plants need more water in winter? No? What happened with the plants during winter? What happened with the birds during winter? Hibernate. Yeah, plants go to sleeping mode. That's basically what happened. So what do you think will happen with the evapotranspiration? If the plants are asleep, what do you think will happen with the water that they require? Will it go up or down? Down. So technically going down, it has to be darker. Am I right? So it's getting darker, they are using less water, and that is November, and that is December, and that is January. What do you think will happen as spring or summer comes up? Yeah, the plants kind of get awake. So it will start becoming greener and greener. And that's something that you were kind of asking in terms of the precipitation. This is also how evapotranspiration changes. It is a function of time. So as you can see here, we're in July, August. So in the peak of July, August, they are using 10 millimeters every day. 10 millimeters, it will be about what? 3/8 of an inch. And then we are going to September. Okay, now this is a comparison of evapotranspiration through different years. So here on the left is 2012, and then on the right is 2010. So this year is dry, this year it's wet. Do you think, okay, wet conditions, what do you think are these 2 years, do you think, are they going to be the same? Does it has anything to do how much water the plants drink depending if it is colder or if it's hotter? When you're in a hot day, do you drink more water than when you're in a cold day? Do you think it will happen the same with the plants? Okay, So we're in November, and yeah, a tiny bit here. Can you see? And then this is getting again wet. Look, this is starting in early spring. Then it start getting hotter. Here by May, this is almost everything is green. It's plants are taking more water. This reference evapotranspiration is larger. So it does change. So a hydrograph, we have a cardiogram, which is basically how you heart rate and how it looks. A hydrograph is exactly the same. I would say that it's a cardiogram of the Earth. It is really what is there. It's a picture of how water changes through time. Basically, so imagine that right now here we have a bunch of rain. So here we have plenty of, okay, so we have rain going this way, which are actually these columns. When it starts raining, the river will not immediately respond. It takes some time until actually all the water kind of gets into the river, and then the river starts kind of raising. And that's what happened here. This is when the river starts raising. We have a big discharge, and then it will go down. This side is called the rising limb of the hydrograph, and this is the falling limb. But that is basically how it looks like. And I'm going to show you another hydrograph that basically tells you how much water is flowing in a particular river. And in this case, this specific hydrograph, what is showing you is like, okay, it rains, and then now that it starts raining, it takes some time for the river to respond. And then how it responds, the river will carry more water, so it will start increasing. And this axis here is the amount of water that the river is transporting. Start kind of transporting more, and then it will come back. Infiltration, it is kind of about the same of infiltration, and the rate of infiltration is kind of the same like when you go back home during Thanksgiving. Basically, okay, imagine that you're going back to Thanksgiving and you're starving. Okay, what is the main activity in Thanksgiving? Eating, okay. Well, and also spending some time with your family, but as part of that is also eating. Okay, so if you go back home, you're starving, and that's Thanksgiving, and you're right to your home, what will happen? Come on, guys. Yeah, you will start eating. Are you gonna eat fast, slow? What will happen? If you're starving, you're just gonna start like, okay, yeah, let me start eating this and this and that. There will be certain times, so you have this kind of rate of eating. But let's say that it already happens 10 or 15 minutes, 20. What will happen? Are you gonna start continue eating in the same rate, at the same velocity? No, it's kind of like, oh, belly's full. So it will start reducing. There will be a point where you say, okay, now I'm stuffed. Give me more. But if you're seated close to the table, what will you do? Let me just grab a bite of this. And that's kind of this part here. It is exactly the same with the soil. If you pour a glass of water, when the soil is dry, it will drink a lot of water. Once it starts getting to the saturation, it's kind of, the soil is full, this stuff, and it will just drink so much, which is this KSAT. So now, let me tell you something here. Okay. Okay. Okay, now here I want to compare two things. So one is the rainfall rate and the other one is the infiltration capacity. Okay, two concepts that I just told you. The rainfall rate is you have this much precipitation falling at a specific time. Okay? Let's say that is raining, just for the sake of having easy numbers, let's say that is 1 inch an hour. So that's how it's raining. And let's say that in this case, the infiltration capacity, the amount that the soil can drink, is less than that one inch. Let's say that is half inch. You have 1 inch raining, and the soil can take only half. What do you think will happen to the other half? Or what do you think will happen? Yeah, you said there. Come on. Runoff. Yeah, direct runoff. So we will have surface runoff. Yeah. Dun, 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 dun. What do you think will happen if in the contrary, if we have 1 inch of rain and then the soil can drink 2 inches? All the water will fall into will go into the soil, so all the water will be infiltrated. Okay, so here we have. Okay, this is the rainfall rate. The amount that is raining is less than the amount that the soil can drink, which is the infiltration capacity. That's why we have all the water going into. Now, notice that once it has gone into the groundwater, into the water table, now all that water will start move into the river. So now the river has to kind of start raising. That's what is called subsurface flow. If we do, where is this? Here. It will take some time, but in this case it's the opposite. When there is way more rain than what actually the soil can drink, we will have surface runoff. So we have surface runoff, we have subsurface flow, and we have base flow. Surface runoff is when the soil is stuck and all the water is going into the surface. Subsurface runoff is when it has infiltrated and now it starts moving into the river. And the base flow is this part when actually the groundwater is, and we're going to see there is in contact or is in connection with the surface water. So there is a balance between how much water is going in the river to the groundwater and from the groundwater to the river. So you can see that when it starts raining, because the river cannot take that much water, it just starts surface runoff. Okay. So this is what I was mentioning. This is direct runoff, subsurface flow, and then this is the base flow. Water that is usually going from the river to the groundwater or from the groundwater to the river. And I'll show you how that happens. And you see that some of these events actually have the form that I was mentioning you of the hydrograph. I mean, that is there. And just consider that the hydrograph again is kind of the cardiogram of the Earth. I know that sounds really cheesy. I'm a hydrologist, sorry. Okay, we'll talk about this later. Now, groundwater. And groundwater basically is all the water that is in the ground and that fills all the pores of the soil. That's what is groundwater. How water moves? Basically, it it moves around of all the particles of the soil. It's not a ghost that passes through it. It actually moves around. There are some rocks that are kind of porous, and it will pass it through. But again, so we have the saturated zone, or the water, when we have soil and water field. That is the saturated zone. The one that is above here is when we have soil, water, and air. So we have those three elements, and that is unsaturated. And when it gets saturated of water, it's called saturated zone. This is also called Beidou zone. The capillary fringe, there are some forces that actually defeat the gravity. One of those is capillarity. So capillarity can move upwards. And this is what is happening here. So the surface tension, so water has certain surface tension. And basically what it does is that the free surface that you see there, if you put a napkin, water will start moving upwards. And basically that surface tension, that surface of the water, when it touches a different surface, kind of grabs it and start moving upwards. It's moving upwards against gravity. So it has the force of the capillarity is greater than the force of gravity. And there are aquifers that are confined and unconfined. So basically the ones that are confined, it's like a sandwich, the ham of the sandwich. If you have an impermeable layer and then an aquifer below, that is a confined aquifer.